All right, let's get started. If you've not seen, I finally have gotten around to started responding back to some of the feedback comments. The thing that was kind of surprising to me when I saw the answer to the first question is that 40% of you are challenged and unhappy, and that is a fairly large fraction, which is not great to say the least. I have one theory for why that is the case, which is that this year the midterm scores were a good third lower than last year. So I'm hoping that is the main reason, in which case it's still okay in the sense that I'm sure you guys will make it up in the finals. And I have a post talking about, how if you, for example, didn't do that well on the midterm, how you can prepare for the final, and specifically the point about time pressure. I believe the finals will not have the time pressure be an issue. Okay. So I'll keep on responding to various sections, and I'll just keep on adding links over here. Any questions or comments before I move on? Okay, if you want to respond, not respond in public, you can send me email. If you want it to be anonymous, you can again go post just on the final question on the feedback form if you have something more to say. All right, so we are now getting to the last kind of leg of the course. So we have been doing this flow chart, like start off with problem statement, design, formulate the mathematical problem, design algorithms, design data structures, and then analyze the correctness or runtime of the algorithms. And the focus of the course pretty much from the midterm on was on looking at various techniques to design algorithms. And in this course, we covered 3 general techniques, of which 2 are done now. So we looked at greedy algorithms. And typically, the examples that we saw, it reduced exponential. The naive algorithms were exponential time and reduce it down to polynomial, sometimes linear or n log n. And in divide and conquer, the examples that we have seen typically reduce a larger polynomial runtime to a smaller polynomial runtime. So we're going to look at the third algorithmic technique, which is called dynamic programming. And there are similarities and differences between dynamic programming and divide and conquer. They are same because both design recursive algorithms, right? So in divide and conquer, you pick your problem, divide it into subproblems, recursively solve it, and patch it together. And so that will also be the case in dynamic programming, in the sense that you will divide the problem into subproblems and recursively solve subproblems. However, the big difference between dynamic programming and divide and conquer is how many of these subproblems you solve. So it turns out in most of the divide and conquer thing, maybe integer multiplication was a slightly different example. But you basically have one problem and you solve a smaller number of subproblems, right? And all the subproblems that you encounter when doing divide and conquer are all different subproblems, right? So you might have, more than linear number of them, but they're all different subproblems. Typically in dynamic programming, if you just do naive recursions, you'll get lots of repeats of the subproblem. So you'll have the same subproblem cropping up in many different places. And the main insight of dynamic programming, above and beyond divide and conquer, is that you should be smart about solving subproblems. So if you've solved a subproblem already, remember the answer so that if you see it again, you don't repeat it. So in that sense, that's the main difference between dynamic programming and divide and conquer. So, thankfully, this is not last week, in which case this would have been kind of cruel. But so here's kind of the problem that I had mentioned that we had looked at a long time back. So again, let's assume this is last week of class, and then you have to write a term paper, study for exams, party, submit your 331 homeworks and do projects. And previously we'd assumed all of them had kind of the same benefit for you, which is definitely not the case, right? So we're going to look at a weighted version of the scheduling problem where now doing a certain task gives you a certain amount of profit, right? So the project might take you an entire week, but it's worth 30 points, whereas 331, might just take you one day, but it's just worth only 3 points. So now, again, as in the interval scheduling problem, at any given day, you can still only solve one job or do one job or schedule one interval. And like in the interval scheduling problem, the start and finish times are fixed, so you can't move them around, like we could for the minimizing maximum lateness problem. But now what we want to do is, instead of just maximizing the number of intervals that we schedule, we want to come up with a schedule that maximizes total profit or value from it. Okay. So, all right, so we have this problem. The first thing to try, because we know that for the case where all the values are the same or all the values are 1, then greedy algorithm works, so which is picking earliest deadline first. And so let's run that algorithm over here. So you pick exam study first because it finishes first. Once you pick exam, you cannot do project or term paper, and then whatever remains is the schedule you would have, that the greedy algorithm would pick. So in this case, the value of the schedule is the sum of the values of the jobs or intervals that you picked, in which case it's 10. And this is clearly not optimal because in this case you should pick project because it's worth 30 points. Okay. So what we want to do is, so basically we want to solve this weighted version of the original problem that we saw. So I'm going to formally define the problem, and then we're going to slowly start working through the dynamic programming version of this. One comment I should make, there are no known greedy algorithms that solve the weighted interval scheduling problem. And this is also true in a strong mathematical self. If you're okay with a certain subclass of greedy algorithms, you can prove that there are no greedy algorithms in that class that can solve the weighted interval scheduling problem. So in that sense, we have to look beyond greedy algorithms, and dynamic programming turns out to be the way to go here. Okay. Any questions so far? All right, so what we're going to do today is I'll formally define the problem just to make sure all of us are on the same page. And instead of diving directly and trying to come up with the final dynamic programming algorithm where you have to worry about whether subproblems are being repeated or not, we'll just try to design a recursive algorithm. Okay, so let's not worry about, at least to begin with, the actual runtime. Let's just try to come up with, is there a way to solve this weighted interval scheduling problem on, say, n jobs in terms of smaller subproblems. So the same problem, but smaller number of jobs. And it turns out that pretty much all dynamic programming algorithms that you do, that's always the first step. So you don't worry, at least at the beginning, try to figure out whether this is efficient or not. Let's just try to see if we can get a recursive definition of the optimal solution to problems. Okay? So that's what we're going to try to do. And towards the end of the lecture, we'll see why, if you are not careful, just doing a simple implementation of the recursive algorithm is going to run in exponential time, and then we'll see how you can do better. Okay. All right. So as I said, so we are going to look at the recursive part for now. All right. All right, so I said this problem is called the weighted interval scheduling problem. And the input, as was the case for the interval scheduling problem, is you have n jobs or intervals such that the ith interval. So in the original interval scheduling problem, it just had two parameters, start and finish, and now we'll have three, start, finish, and value. Okay. So you have the start time Si, finish time Fi, and the value Vi. So again, this is the start time, this is the finish time, and this is the value that you'll get if you schedule this interval. Okay. So recall the convention that we think of the intervals as, starting from time Si, but it has to finish strictly before Fi. Okay, so the actual finish time has to be Fi minus 1. And your output is a schedule which is a subset of the intervals, and by definition schedule means there is no conflict. And the definition of conflict is exactly as it was for the interval scheduling problem. Two intervals conflict if they overlap, if you draw them out on time. So you want a schedule that maximizes its value. And the value of a schedule is you just look at all the intervals in the schedule and just add them up. So note that if you look at the original interval scheduling problem, this is the case where the value of all the intervals is 1, or equivalently the value is the same. Right? So as long as the value is the same, what really matters is how many of them you pack. But again, this is the more general version, and we know that if we ignore the values and just try to maximize the number of jobs that you can pack in, then you will not get an optimal solution. So you will not get a solution that maximizes the total value. Are there any questions on the problem statement? Angus. V of S. Yeah, last year I used to write V like this, and then everyone's like, why is there a square root there? So I'm not going to do that. So is everyone okay with the problem statement? Everyone okay with why if we apply the greedy algorithm for just the interval scheduling problem, it won't work? Okay, so what we're going to do next is kind of try to, as I said, we'll try to come up with a recursive formulation of the problem. And this step is pretty much true for all dynamic programming algorithms. What you do is you try to reason about the optimal solution to the problem on. So in this case, we'll try to reason about the optimal solution on n intervals in terms of optimal solutions on smaller number of intervals. Okay? And it so turns out that in this case, you always will think of the optimal solution from 1 to n in terms of something that's 1 to something that's smaller than n. Okay? And there might be more than one such things, but the sub-problems are always starting from the first guy to some guy which is strictly smaller than n. Okay? And to kind of build the intuition for what to do this, how to do this, we're going to look at a specific example with 5 intervals. I'm not going to specify the actual deadlines or start times or even values, just so that we kind of do it at a slightly abstract level. But it will be drawn out, so it's hopefully concrete enough so that we can follow. And that what we're going to try to do is try to see what can happen or what can we say about the optimal solution to this input with 5 elements. Okay. So here's an exercise with n equal to 5. And so I'm just drawing. So this is, so I'll draw the indices are with respect to an increasing order of finish time. So the last guy to finish is this guy. This is the fourth last guy to finish. This is the third last interval to finish. This is the second last interval to finish. And finally, this is the interval that finishes first. Okay, so what's more important is to figure out, is to keep in mind which jobs conflict with each other or not. Okay. And of course, I mean, what we're going to do is, again, like we had done when we were analyzing greedy algorithms, we said, well, let's just look at an optimal solution and then somehow try to reason about how the output for the greedy is related to that optimal solution. Okay. So here we have no algorithm to compare with, right? But we'll still put an optimal solution out of the hat and then try to, as I said, reason about the optimal solution itself. Okay. So only use the definition of the problem to reason about the optimal solution. Okay. So let O be an optimal schedule for the entire input. So I'm saying look at all the first 5 inputs. And typically the way the dynamic programming works is you just do, at the beginning, do like cases, right? So you just say, is this guy in the optimal solution or not? Because that's typically the simplest one. And you can start it in various ways and various, which, so in this case, I could talk about, is 5 in the optimal solution or not? Is 4 in the optimal solution or not? Is 3 in the optimal solution or not? And typically, which one you start off with needs a bit of art. So in this case, we'll just start off with the 5th guy. Okay. So what we're going to look at are 2 cases. Either the 5th interval is in the schedule or it's not. I mean, there are no other possibilities. Okay. So let's look at those 2 possibilities and try to do some more reasoning. Okay. So the first case is we're assuming that the last guy is not in the optimal solution. If the last guy is not in the optimal solution, then just trivially it follows that the optimal solution only picks intervals from the first 4 intervals, right? Because there are 5 intervals and you said I don't have the last guy. Okay, so the interesting aspect of this is we're going to argue, well, not only is it the case that this O has intervals only from 1 to 4, it will actually be an optimal solution from 1 to 4. Okay. So we're going to claim O is an optimal solution to 4. Okay. So we are saying something stronger. So we're saying if 5 is not there, then whatever remains actually has to be an optimal solution for the subproblem, which only had the first 4 intervals in it. So it's not that hard to argue, so we'll quickly go over it. So the first thing to observe is, by definition, an optimal solution cannot have any conflict, right? And so we're saying O only contains elements from 1 to 4. So this implies O is actually a valid schedule from 1 to 4. Okay. So since O does not have any conflicts. O is a schedule for the smaller input instance when you only have the first one. Again, this just follows by pretty much by definition. So now what we want to argue is not only is it a valid solution, but it has the largest possible value. Okay. And so to argue that it has the largest possible value, we'll do a quick argument by contradiction. Okay. So for contradiction, assume there exists an O prime, or when I say there exists a schedule O prime such that its value is more than rho. Okay, so for contradiction we assume, let's say O is not an optimal solution 1 to 4, then that means there has to exist another schedule O prime which has strictly larger value. But then then the observation is, well, then O prime is actually a valid solution for everything also, and you have a valid schedule for everything which has a larger value. But O prime is also a valid schedule for 5, and so this in particular implies this contradicts the assumption that O is optimal for the original problem. So, like maybe a one-sentence summary of all of this is saying, if we assume 5 is not in the optimal solution, then you might as well have just started with an input that didn't have 5 in it. Okay. Are there questions on this? Do you guys want to talk about this, or should I move on? Okay. All right, let's move on. So we have considered the case where the last interval was not in the optimal schedule, and then we concluded that the original schedule is actually optimal for just for the first 4 instances. And now we're going to look at the other case where things get more interesting. So case 2 is is in the optimals. Okay. So if I pick 5, which 2 intervals do you know for sure cannot be in the optimal solution? 3 and 4, right. So if 5 is in the optimal solution, it conflicts with 3 and 4, and they cannot be in the optimal solution. Okay. So that implies 3 and 4 are not an optimal solution, as 3 and 4 conflict with 5. So the second claim that we are going to make is that if I know now that 5 is in the optimal schedule, so if I throw away 5, then I'll claim that the schedule that I get by throwing away 5 is optimal for all the intervals that do not conflict with 5. So this is an optimal schedule. In this case, whatever remains is just 1 and 2. Okay. And the argument will pretty much be the same as before. The only extra thing now is we have to take care of 5 and 3 and 4, which conflict with 5. Okay, but the argument again would be similar. So let's do the argument again. So the first thing to note is by the fact that 3 and 4 are not an optimal solution, we have that if you throw away 5, then whatever remains can only be a subset of 1 and 2. And the second is, by definition, if you have a schedule that doesn't have any conflict and you throw intervals away, you'll get another schedule that has no conflict in it. So optimal minus 5 has no conflict. And so both of these imply that the schedule where you drop 5 is a valid schedule for 1 and 2. Valid schedule for 1 and 2. Okay. And now what we want to argue, as I said, is, so we know that it's a valid schedule, and now we want to argue that it is indeed an optimal schedule. And the way we'll do it is again by contradiction. We'll assume that, let's say there was a better solution for 1 and 2 than what you get from throwing away 5 from O. Then what you do is just replace, you take the optimal schedule for 1 and 2, add 5 back. You'll get a valid schedule for everything, which will now have a larger value. And so that will be a contradiction. So let's walk through that argument too. So for contradiction, assume exists schedule O prime for 1 and 2 such that this guy has, so that O prime is a better schedule for 1 and 2 from the schedule where you drop 5 from O. And so once you have this, with this assumption, few things to note. The first thing is that if you add 5 to O prime, then this is a valid schedule for all the inputs. And again, the basic thing is, as 5 does not conflict with 2 and 3. Sorry, conflict with 1 and 2. Conflict with 1 or 2. And since it's a valid schedule, just let's look at what's the value of O prime plus 5 is just the value of O prime plus value of 5. We know that the value of O prime is strictly more than value of O minus 5. So this is strictly more than value of O minus 5 plus value, plus value of 5. This is same as value of O. And so this contradicts the optimality of O for the entire input. So contradicts optimality of O for everything. So what we have done is we looked at two cases whether 5 is in the optimal or not, and in each case we know something more about another subproblem. So in the case that 5 is not in the optimal, we know that our original optimal solution is also the optimal for 1 to 4. Or put another way, if you think of it in reverse, if 5 is not in the optimal solution, then the optimal solution is an optimal solution for 1 to 4. If 5, in the other case we've argued, if 5 is indeed in the optimal solution, then if you drop whatever remains in 5, then what you get is actually an optimal solution for 1 and 2. In both cases, you have kind of have some more idea about the optimal solution in terms of optimal solution for smaller problems. So what I want to do is talk to your friends for half a minute. Let me know if you have any questions on whatever we have concluded for these two cases. Once you're okay with this, we are almost there. We'll come up with a simple way to combine these two to come up with a recursive formulation. And then it's just a matter of kind of generalizing this, which is fairly simple. Okay. Are there any questions? Mehmet.
So you're doing, you're saying that if you include 5 in the schedule, then you're saying that, or you want and then you're saying that 5 is also not going to enter the optimal schedule, and there's 2 elements, 2 schedules.
No, what I'm saying, so you're asking about this claim?
Yeah.
So what this is saying is, O is an optimal schedule from 1 to 5, and it also has 5, right? So what I'm saying is throw it away. You get a smaller schedule which doesn't have 5 in it. And that will be an optimal schedule for 1 and 2.
Okay. Yeah, that's what I was looking at, is the 2, like the box around 2. Is that saying like how many intervals are?
Oh, so sorry. So this is, okay. So this is shorthand notation that we have used. This is just the set from 1 to m. So box around a positive integer is a notation that's the set of numbers from 1 to that integer. Does that make sense now? Any other questions? Okay, so let's move on. And so now what we're going to do is combine these two and get kind of one nice recursive formulation for the optimal solution. And so the first assumption we're going to make is kind of simplify the problem. So ultimately, of course, we do want the actual optimal schedule. But for the time being, let's say we are okay if we just knew the value of the optimal schedule. Right? So this is kind of similar to what we did for Dijkstra when we're trying to design Dijkstra's algorithm. Instead of trying to figure out the smallest, the shortest path, we're saying let's just tell me the distance and I'll be happy with it. Okay? And then we saw that once you have designed Dijkstra's algorithm, from that information you can recreate the actual pair of the actual shortest paths. So we're going to do something similar. We're going to just make the problem simpler, but just trying to compute the value of the optimal solution. And then later on, we'll see once the algorithm is run, how you can actually compute the actual optimal solution. So we're going to assume, at least for now, only care about the value of the optimal solution. And as I said, we will later see how to compute the actual thing later. Okay. And again, this just makes our kind of thought process easier. We just have to keep track of one value instead of a set. But we'll see how we can handle that. All right. So with this, we need another notation. So we'll denote opt of I to be the value of the optimal solution for the input instance where you only have the first eigenvalue. So note that our goal is to compute opt of n. We want to know the final optimal value. All right, so let's go back to our example for n is equal to 5. Maybe I'll do this so that at least kind of see where this is going. So what we have seen is we wanted to look at opt of 5. That's what we're interested in. But we looked at two cases. The first case was 5 is not in the optimal solution, in which case we figured out the optimal value of 4 or 5 is exactly equal to the optimal value of 4. Right? Because we said that the opt for 5 is actually an optimal solution for 1 to 4. Okay. In the case where 5 was actually in the optimal solution, then the value of this, of course, we get the value from picking the fifth guy. But then whatever remains is the optimal solution for a smaller problem. So what should I put in here? So if 5 is in the optimal thing, then opt of 5 is V5 plus opt of what?
Whatever doesn't conflict with 5.
Which is what? In this, which is 2, right? And the important point to note is either 5 isn't optimal or not, right? So what is the, so if I were to combine these two into one equality of opt 5, okay, I want to combine these two using one kind of operator here. What should I put in here? Max, right? So you want the largest values. You know these are the only two possibilities. So the overall optimal would be the max. Okay. Okay, so here's our kind of the recursive formula for first step. This doesn't quite give us the entire recursive formula, because to get the final recursive formula, instead of saying opt of 5, we should be saying something like opt of j for arbitrary j. How does it depend on smaller opts? Okay, but is everyone okay with this formula for now? Yep. All right, let's now move on. And so our goal is now to generalize this for arbitrary instances and for arbitrary n. Okay. All right. So what we're going to do next is extend this logic to a general value of n. And since we want general things, we need more definitions. So let O of j be an optimal solution for the inputs on the first j intervals. And then note, by definition, this implies opt of j is just this value of this O of j. Okay. All right. So the first thing is, and what we're going to do is, I could have started from n as we did in previous case was n equal to 5. But the point is, the argument that I'm going to make should work for any input instance from 1 to j. So just pick any j. Okay. So fix any j. And the first case we want to see is when j is not in the optimal solution from 1 to j. In this case, using the same argument as before, what you have is actually an optimal solution from 1 to j minus 1. So in this case, opt of j is same as opt of j minus 1. And the argument that I did for j equal to 5 is exactly the same. You just replace 5 by j and just 4 by j minus 1, and you'll get exactly this thing. All right, so this was easy enough. The second case is when j is actually in the optimal solution from 1 to j. And now we need to, in the previous case when we had a specific example, we said 5 is in the optimal solution, let's just figure out all the jobs that conflict and throw them away. So what we need to do is figure out a way to, given j, figure out which guys conflict with j. Okay. So what we are going to do, and I realize I forgot to say something that I should have earlier. So let's assume that my input is such that the jobs are sorted by finish time. Okay. So f1 less than equal to f2, all the way less than equal to f1. And if it's not, as usual, you can sort and get it. So if not, sort in order n log n time. Okay. All right. And so what we now need to do is figure out a way, given j, figure out which are the jobs that conflict with j. And so for that we need another definition, which is let p of j be the largest I that's strictly smaller than j such that I and j do not conflict. Now it is possible that there might not be such an I. For example, if the job is the very first job, in this case we'll just give it a default value of 0. Okay. And if no such I exists, p of j is just 0. So kind of to help you settle the definition in your head, I'll just go through an example. I'm actually using the example from the book itself. So this is an example with n is equal to 6. Here's the first interval. Here's the second interval. The third interval. The fourth interval, which starts right after 1, but before 3. Then I look at the fifth interval, which starts after this, and then I have the sixth interval, which. Okay, so here's an example with 6 intervals, and what I want us to do is just kind of quickly go and figure out the p-values for all of these. Okay. All right, so what is p of 1? No, so it's you need to find the largest I that's strictly smaller than j.
It's nothing.
It is nothing, so it by default goes to value of 0. Okay, good. P of 2. Zero. Great. P of 3. 1. P of 4. 1. P of 5. I should have drawn this better, shouldn't I? Let's say it starts here. So 2. And then P of 6 is also 2. Okay? All right. Now, why is this interesting? This is interesting because of 2 reasons. And I'm going to leave this as, I'm not going to argue this, but something for you to go back and convince yourself is true is a good exercise to make sure you understand this definition of P. So the first thing to note is everything that is strictly between P of j and j has a conflict with j. Okay? So the first thing is P of j plus 1 all the way up to j minus 1 conflict with j. Right, so in the previous example, this was 3 and 4. Right, so you figured out which are the ones that conflict with j. And not only that, it's also the case that none of 1 to P of j conflict with j. What this means is if we throw out j and all the intervals that conflict with j, you will be left with 1 to P of j. Okay. So this implies opt of j is you have the jth guy in, right? So I'm assuming j is in the optimal solution, so that's equal to v of j plus opt of p of j. And again, the argument for this is the similar one where we argued that if you drop 5 from the optimal solution, you will get an optimal solution for 1 and 2. So it's the same thing. If you drop j from O of j, you're going to get an optimal solution from 1 to P of j. Okay. And so then overall, you'll get opt of j is the best of the 2 cases. So in one case, we get opt of j minus 1. And in the other case, we get opt of pj plus v of j. And now note that we have a true recurrence now. Right, so you can keep on applying this, and you will get opt of j defined in terms of smaller and smaller subproblems. Okay? So of course we need a base case, but the base case is kind of trivial. Opt of 0 is 0. If you don't have anything, you don't get anything. So base case opt of 0 is 0. And we are done. So we have now a complete recursive definition of the value of an optimal solution on the first j guys in terms of the optimal value for j minus 1 and the optimal solution for P of j. Okay. So so again, I just restated this recursive formula. And this always is the first step in all dynamic programming algorithms. You try to come up with either the value, typically it's the value of the optimal solution or on n, recursively in terms of optimal for smaller problem, smaller problem instances. And so again, remember the first, sorry, I switched the order of the maxes over here. So the first term comes if j is in the optimal solution, and the second term comes if j is not in the optimal solution. Okay. So now let's say someone tells you the value of all of opt of 1 up to opt of j minus 1. Okay. Can you quickly figure out whether j should be in the optimal solution or not? Or what would be a simple check to decide whether j should be in the optimal solution or not? Mehmet. No, so all I'm telling you is I'm telling you the opt values. So I've told you opt of 1, opt of 2, all the way of opt of j minus 1. And I want to, now what I'm saying is, and I tell you that this reconciliation is true, what I want you to tell me is a quick way to check whether j is in the optimal solution or not. Matt.
Calculate P of J and then look up the two options.
Right, so then what you do, so remember, if j is in the optimal solution, then this is what happens, otherwise this happens. Right? So what you do is, since you know all these out values, compute this value, whichever is bigger, that's the case that happens. So in particular, if this parameter is bigger, that means j is in the optimal solution. If this parameter is bigger, then j is not in the optimal solution. What happens if they are the same? If they are the same, it doesn't matter. That means there is one optimal solution that has j in it, another optimal solution that does not have j in it. So, and so the idea is, if I'm able to recursively solve for opt of 1 up to opt of n, just knowing all those values, I can actually compute the actual optimal value by just keeping recursively applying this check. Okay. All right. Sorry for going over a bit. On Friday, we'll start from here.